All right, this is Unit 4, the Atomic History and Structure Review. So I'm going to do a brief overview of what we should have learned again from the previous year. The first thing we have here is an atomic history review. This is a list of names and experiments that you should be familiar with. On my website, there's a link to a Google Doc that has several resources for you to look at for each of these. And you can also use your textbook. There's a couple of them that aren't well defined in your textbook, so you may want to go to the Google Doc and look up a few of them. The first grouping here is the early chemistry work, so that talks about kind of the origins of chemistry, some basic information. Then we have the parts of the atom, when they were discovered and how. Equations, properties of light and photons, that was kind of in between there, and then we have the quantum model. The first two groups there are mostly found in Chapter 2, and then the last two groups are found in Chapter 7. You should have a brief description for each of these bullets, and then a brief understanding of kind of what they did, what was important, and that kind of information. We'll have a quiz on this information shortly after we start the unit. So I'd probably say a sentence or two about each of them, maybe a diagram if you feel that's appropriate. And that's about it. From our early understanding of the atom, we know that each atom contains 3 subatomic particles. You guys should all be very familiar with this. The 3 subatomic particles are protons, neutrons, and electrons. Some basic information about each of them. You have the mass, charge, and location. Protons and neutrons both have a mass of 1 AMU, and AMU stands for atomic mass unit. Again, that's a relative mass. So protons and neutrons essentially have the same relative mass, and electrons are very much smaller than that. So when you're talking about the mass of an atom, really it's just the protons and neutrons that you are concerned with. For charge, protons have a charge of +1, neutrons are neutral, and electrons are -1. So unlike mass, here electrons play a very big role and neutrons don't really. So we're talking about the charge of an ion or charge of an atom. It's really the protons and electrons that we're dealing with. For location, protons and neutrons are located inside the nucleus and the electrons are located outside. So when we're dealing with chemical reactions, it's really just the electrons that are going to be playing a role since the nucleus tends not to be involved. Protons are very important because they are what determines the identity of an atom. Only carbon can have 6 protons. If it has 6 protons, it can't be anything other than carbon. So that is kind of the defining characteristic for each element, the number of protons the atoms have. The neutrons and electrons can vary, whether they're isotopes or ions, but the protons must remain a constant. Some important terms. The first one is atomic number. That's the number of protons in an atom. You'll see that I've given you the representation for each element that's found on your AP periodic table, just to make sure you're not getting it confused with what we used in our previous courses. So again, that top number there is the atomic number, the number of protons. The second term is a mass number. This is the mass of each individual atom. It's the number of protons plus the number of neutrons, and it should be a whole number. Why again is there no mention of electrons in the mass? That's because electrons are so much smaller, they won't really have an impact on the mass until there are 1,836 of them, and obviously no atom has that many electrons. Isotopes, again, are atoms of the same element with a different number of neutrons and therefore a different mass number. So we have carbon-12, carbon-13, carbon-14, those are all isotopes of carbon. Since the number of protons can't change, because that's what defines what carbon is, it's the number of neutrons that are changing the mass, because those are the only two things that play a role in the mass of your element. You'll notice the atomic weight that's given to you, though, is not a whole number. It's not a whole number because it's the weighted average of all the naturally occurring isotopes for the element. So sulfur has an average mass of 32.06, so that should always have some decimal information. If you look at carbon, I believe it's 12.01, which tells you there's got to be a little bit something different in each sample of carbon. So there's a small amount of carbon-13, carbon-14, and there's a relatively large amount of carbon-12. Now how do I know the relative amounts? I know that because it's a weighted average. So if carbon's average atomic mass is 12.01, then the majority of that sample was carbon-12 atoms, and there's a small amount of the other 2 isotopes. If there were more carbon-13 in the world, then the average atomic mass should be closer to 13. So if you look up at sulfur, you'll see that since the mass is 32.06, and probably the most common isotope is going to be 32, and there will be some isotopes that are definitely heavier than that to account for that 0.06 extra. All right, so how do we use this information? We use it to mostly find the number of protons, neutrons, and electrons. So first, the number of protons. The atomic number is the number of protons, so that would be 16 for sulfur. The number of electrons in an atom, which is defined as neutral, meaning it has to have no overall charge, the number of protons must equal the number of electrons, so that should be 16 too. An ion would have a different number of electrons than protons. If it was going to be a positive ion, it should have less electrons. If it's a negative ion, it should have more electrons. The number of neutrons, if you're only given the atomic mass or the information from your periodic table, you need to round that atomic mass to the nearest whole number, because you can't have a fraction of a proton or a fraction of a neutron in your actual atom. And then you subtract the number of protons. So for sulfur's case, you would round it to 32. You'd do 32 minus 16, and that would be 16 as well. If you're given a specific isotope number, like sulfur 34, then you would use that number instead of rounding the atomic mass. You can also make a pretty good guess about what the most common isotope is based on the value for the atomic mass. For sulfur, it's most likely to be 32 because that's what it's closest to. For phosphorus, it would be most likely to be 31, and again, because that's what it would round to. So we have two practice problems here. So I'd like you to determine the number of protons, neutrons, and electrons in an atom of bromine given the information from your periodic table. And then I'd also like you to determine the number of protons, neutrons, and electrons in this particular atom of chlorine. So if you want to pause for a second and then try that. Okay, so for bromine, your protons would be 35 because that's the atomic number. To get the number of neutrons, since I didn't give you a specific isotope number, you would round the mass given, 79.90, to its nearest whole number, which would be 80. And then you subtract 35 from 80 to get a neutron number of 45. Electrons, since it's an atom, should be the same as protons, so that should also be 35. For chlorine, here I have given you a specific isotope number, so you're going to use that in place of the average atomic mass given to you on the table. But you are going to need to look up the proton numbers, or the atomic number. So when you do that, you find that protons are equal to 17. Your neutrons, again, you're going to subtract, but you're going to use the 37 provided. So 37 minus 17 is equal to 20. And then your electrons should be the same as your protons, which would be 17. This is a quick review of the models you should remember, hopefully, from your previous course. You should be able to draw and recognize images of these two models. The first one we have is the Bohr model. The Bohr model has 7 principal energy levels, or rings, around the nucleus. Each principal energy level has a different energy value, and you'll notice that the energy is different based on the distance from the nucleus, and that distance will vary within the rings. So the distance between 1 and 2 is different than the distance between 2 and 3. So it's not the same increment you're increasing by. Each principal energy level has the certain number of electrons allowed, and you fill them in order of energy. So you'd start with 1 and then work your way up. So principal energy level 1 is only allowed 2 electrons. Principal energy level 2 is allowed 8 electrons. Principal energy level 3 is allowed a total of 18, and then principal energy levels 4 through 7 each have 32. To move from one energy level to another, you must gain or lose a quanta of energy. And when you absorb that energy, you move away from the nucleus, and when you release that energy again, you move back towards the nucleus. When an atom absorbs a quanta of energy, it will move further away from the nucleus, and when this happens, the atom is said to be excited. This is a very unstable state, and the electrons will release the extra energy quickly, usually in the form of light, and that's what produces the atomic spectra for each element. Since the distance, or the energy quanta, is different for every element, that's why the atomic spectra is also different, because those absorbings and returnings have different energy values, so they'll also give off different wavelengths of light. This image is kind of cool because it shows you how the absorbed photon or energy source would come into the electron, would force it to move up to a higher energy level, and then when that electron returns back to its normal ground state, the photon would also be released. It should be absorbing and releasing the exact same quanta of energy. In the modern model, or the quantum mechanical model, instead of having specific set orbits that the electrons travel on, the electrons are instead located in orbitals, which have different shapes and sizes. An orbital is a region of space where the electron is likely to be. There are still 7 principal energy levels, but they are now divided up into these different orbital types. This image shows 3 of the 4 orbital types. So there's an S, a P, a D, and then there's also an F. Each principal energy level is only allowed a certain number of orbitals. So the first energy level only has an S. The second energy level has an S and a P. The third has an S, a P, and a D. And then 4, 5, 6, and 7 have S, P, D, and F. Because each orbital has a different amount of energy, they can fill out of number order. So for example, 3D actually has higher energy than 4S, so 4S would fill first, and then it would go back to fill in the 3D before going back to fill in 4P. How does this connect to the arrangement of the periodic table? So there are certain blocks on the periodic table where those different orbital types are being filled in with the highest energy electrons of that particular atom. So the first block is called the S block. That's the group 1 and 2 elements. So they are filling in that first orbital for the energy level. The P block, you'll notice, kind of skips over the center and starts on the other end. So that fills in the next orbital type. You'll notice in the last row there, that's when the P block is filled, and that's why the noble gases all have 8 total valence electrons. Now, as I mentioned, the 3D is actually of higher energy than the 4S, so it actually fills after the 4S, which is why it's in kind of the middle of the table there, and that's called the D block. Those are the transition metals, and they have some unique properties because of that 3D and other D filling. And then at the bottom are the F block elements, and those are the lanthanides and the actinides. On the last slide here, we have some pictures of the different orbital types, the shapes that they have. So we have an S, which again is a sphere, a P, which is kind of a dumbbell shape, and there are 3 Ps, 1 on each axis. Each orbital can hold a total of 2 electrons, so the S can only hold 2 because it's just that one sphere there. The P can hold a total of 6, so there's 2 in each of those dumbbells, 1 in the PX, 1 in the PZ, and 1 in the PY. There's 2 electrons in each of those orbitals. We're only really going to be concerned with the S and P orbitals for this course, but I wanted to show you the Ds and Fs as well. So as you can see, the shapes get a little more complicated as the orbitals go up in energy. D, there's a total of 5 orbitals. That's a total of 10 electrons that can go in there. And then F has a total of 7 orbitals, and that's a total of 14 electrons. If you go back to the Bohr model, the first energy level in the Bohr model can only have 2 electrons, and that's because it only has an S, which only holds 2. The second energy level has a total of 8 electrons. It's the S and the 3P, so again, that's a total of 8. So the total number of electrons allowed per level doesn't change from the Bohr to the quantum mechanical model. It's just where the electrons are specifically that is different. Okay, that's the end of the review. Your homework should be posted on the Google Doc where the bookwork assignments are listed, so you can certainly get started on that. Don't forget to do your atomic history notes so that you have those for the quiz. And that's it. Good luck.